purpose, so that here is no generator shaft is removed, and then a dynamometer is provided here. Dynamometer, that is a power absorbing device. It absorbs power from the turbine shaft. Here turbine shaft and dynamometer is coupled here, and by applying load on the dynamometer we can measure how much power, output power, is available here. Here in this setup, here is no dam. Here water is taken from the sump. For that we need a pump to supply water. For that here we are using a centrifugal pump, a rotodynamic pump we are using. Here we cannot use the positive displacement. We are, in order to provide a constant discharge, here centrifugal pump is used here. In order to start that pump, initially we have to prime it. For that here a vending provision is here. Here two vending provisions are here, because it is a double suction type. Double suction pipe means water entering from both sides. So that here two knobs are provided. When you after opening these two knob, and then we have to open this plug using pipe wrench. After that we have to pour water. When we pour water, that water fills the suction pipe and a casing and a portion of delivery. After discharging all the water, after releasing all the air, then a continuous flow of water flowing from this side, and after that we can close it. Then close the plug also. That is the priming procedure. Then after that, this is a centrifugal pump. So at the time of starting, this delivery valve should be completely closed to reduce the starting torque. After developing certain head, then we have to open it, and then that water flowing through this pipe, this one we can conduct. This is the penstoke. And in order to measure the quantity of fluid flowing through that penstoke, here a flow meter that is provided here, in which we have to note the time for 100 liters of water. Using a stopwatch, you have to note the time of 100 liters of water. That is, here it is 0.1, 0.2, 0.3, that is marked from 0.1 to 0.2. That much time you have to note. And after that, we have to maintain a head here. It is a constant, it is a high head turbine. Here that head is 150 feet. So we have to maintain this head here. For maintaining that head, by controlling this wheel, we can bring the needle to 150. So at the time of experiment, this needle should be at 150 head. That you should maintain. And also we have to run the turbine at rated RPM. Here the rated RPM is 1000. Now the turbine is running at no load condition at a rated RPM and 150 head. In this condition, first we have to note time for 0.1 meter cube discharge, and and also we have to check the speed. Here this tachometer not working, so you have to use one non-contact type of tachometer here. Check the speed, whether the speed is 1000 and the head is 150. Note the time for 0.1 meter cube discharge. Then after that we can apply the load. Initially, before starting the experiment, we have to find out how much is the maximum load that can be applied there. We know that power P equal to T omega, that is omega is 2 pi n by 60, and T is the torque. So power P equal to 2 pi nt by 60. Here power P equal to 5 HP. In SI unit, that power is in water. So we have to convert into water. 1 HP is equal to 746 watt. So 5 into 746 is equal to 2 into pi into n. N is the rated speed, that is 1000. And torque, in order to measure the torque, here dynamometer is provided. In that dynamometer, this is a rope drum dynamometer, a rope that is wound around the drum. And here, in order to measure the tension, here two spring balance that is provided here. That spring balance, which is in LB, that is in pound. That is LB. That is 1 LB, that is equal to 0.454 kg. Here is one tension and here is another tension. So S1 and S2 is the tensions. So S1 minus S2 is the effective load. That load is in kg. So S1 minus S2 into 0.454, it is in kg. And then in order to convert that into Newton, multiply it with 9.81. So S1 minus S2 into G into torque, that is Newton meter. Load is in Newton, and R, that is radius of the drum, that is R, that is in meters, divided by 60. So from which first we have to find effective load S1 minus S2 max, that is maximum load, that is equal to 5 into 7, 46 into 60 divided by 2 into pi into 1000 into G 9.81 into radius of the brake drum. Here dia of the brake drum is, that is in the specification, that is 1 foot. That is 1 foot is equal to 12 inch. 1 inch equal to 2.54. So 12 into 2.54, it is in centimeter, divided by 100, then it is in meter. So 0.304 meter. And radius is equal to half of that, that is 0.15 meter. So in order to find S1 minus S2, 5 into 746 into 60 divided by 2 into pi into 1000 into 9.81 into 0.15, from which we can find out the maximum load. That maximum load, that is in kg, but here it is in pound. So that kg divided by 0.454, that is in LB. Now here the maximum load may be 51 or 52 LB, that you have to calculate first. After that you can prime the pump and then start the experiment. After priming, when the water is flowing, check the speed and head here. If it is speed is 1000 and head is 150, note the time for 0.1 meter cube discharge. After that we can apply the load. Here we already calculated the maximum load. Suppose if it is 52 lb, then while applying load, speed of the turbine decreasing. So before taking the load, initially you have to supply more quantity of water so that the turbine speed we can maintain above the rated speed. So by controlling this wheel, we can control the quantity of water, that is the spear movement, that is taking the spear backward. So more quantity of water striking on it so that the turbine speed become more than rated speed. Suppose the speed now it is 1200 and head is 150. Then after that you can apply the load by simply rotating this wheel. And also before starting you have to check whether this rope is in the loose condition. Then if there is any load, you have to release that load before starting. Starting and stopping must be at a no load condition. Then while applying load, speed on the turbine, that is decreasing. When the speed becomes 1000, check the head also. The speed 1000 and head 150. Then you have to note the time for 0.1 meter cube discharge and spring balance reading S1 and S2. In such a way, before applying load, initially you have to supply more quantity of water so that the turbine speed become above rated speed. And after that, simply apply the load. In such a way, increase the quantity of water and then apply the load. When the speed become 1000, note that the spring balance reading S1, S2 and a time for 0.1 meter cube discharge. In such a way, you have to take a minimum 6 or 7 set of reading, and finally, in order to take the last reading, open these two valve, this globe valve and this wheel valve maximum. So maximum quantity of water is striking on the turbine blade, so that the speed of the turbine is maximum. And after that, you have to apply the load. While applying load, that speed decreasing. When the speed become 1000, note the spring balance reading S1 and S2 and the time for 0.1 meter cube discharge. Okay, after taking all that readings, then release the load. Starting and stopping must be at no load condition. So release the load. While releasing load, there is a tendency, that is the tendency to increase the speed. So in order to maintain that speed at a rated, so you have to reduce the quantity of water by taking the spear that is backward by controlling this wheel. So by controlling this one, we can reduce the quantity of water and also release the load so that we can maintain the speed at a rate. And after releasing all the load, then simply switch off this one. That is initially after priming, then you have to switch on this green button. Then it is the starting condition. Then water is after priming, then you have to switch on this green button. Now the pump is running and that water is passing through this one. Calculate the different quantities. Here, suppose you noted the time for 0.1 meter cube discharge is suppose 20 seconds. And S1 and S2 spring balance reading suppose 38 lb S1 and suppose 5 lb S2. And after that, we know that here the input power of the turbine is output power of the pump. That is, pump supplies water to the turbine. So input power of the turbine is output power of the pump. Output power of the pump is rho GQH. That is rho density of water 1000, G 9.81, and this Q is the discharge. For finding that discharge, we noted the time for 0.1 meter cube discharge. So 0.1 divided by corresponding time. Suppose here it is 20 seconds and H is the head. Here head I already mentioned in the specification it is 150 feet. So that 150 into 0.305, then it is in meters. That power is input power is in watts. And then output power we have to find, that is output power, that is here the turbine shaft rotating, that rotating power, that is T into omega, that T omega is 2 pi n T by 60. So 2 into pi into n 1000 and T torque. For calculating that torque, we noted that spring balance reading, that is S1 38 minus S2 5. This is in LB. So convert that into kg. So multiply it with 0.454. It is in kg. That we have to convert that into Newton by multiplying 9.81 and the radius of the brake drum 0.15 divided by 60. That is also in watts. And then we know that efficiency, that is efficiency is the ratio what we wanted to what we have to pay for. Here we need output power, we have to pay the input power into 100, then percentage efficiency. After calculating that percentage efficiency, then we have to plot a graph. While plotting a graph, in the abscissa, in x-axis, we have to mark the independent quantity. Here independent quantity, here we are changing the load. Based on that load, we can calculate output power. So here the output, that is the independent quantity, that is output power or load. And here dependent quantities in the y-axis, here that is we can mark input power and efficiency that we ought to take in the ordinate y-axis. Then output power versus input, that is output power versus efficiency curve, that is like this, and output power versus input power graph is like this. These two graph you ought to plot. First on impulse turbine, that is hydraulic machine. I already mentioned the hydraulic machine which convert the hydraulic energy of the fluid into mechanical energy, that is pressure energy of the fluid converted into mechanical energy. These turbines are classified based on, that is different classification. One particular classification is based on the energy available at the inlet of the turbine, energy available at the inlet. Based on that, the turbines can be classified into two groups. One is the impulse turbine and other one is the reaction turbine. Energy available at the inlet of the turbine is completely kinetic energy. That turbine is called the impulse turbine. Energy available at the inlet of the turbine is partially pressure energy and partially kinetic energy. That turbine is called the reaction turbine. And also another classification based on the head. Based on head, turbines are classified high head turbine, medium head turbine and low head turbine. High head turbine means head is more than 250 meters. 250 meters maximum head, that is 1770 meters. Medium head means the head is in between 60 and 250 meter. 60 meter to 250 meter. Head is less than 60 meter, it is called low head turbine. Less than 60 meter. In turbine, hydroelectric turbine, for the production of hydroelectric power, water is storing by constructing dams across the river. Then level of water in the dam, that is called head rise. And this water is taken from dam to powerhouse using large concrete or steel pipe. That pipes are called penstoke. In the case of impulse turbine, at the end of the penstoke, a nozzle is provided. So when the fluid passing through this nozzle, pressure energy converting into kinetic energy. So energy available at the inlet of the turbine is completely kinetic energy. That high velocity jet strikes on the blades which are mounted on the periphery of the wheel. Suppose this is the runner wheel. On the periphery of the runner wheel, buckets are provided. All the buckets are double hemispherical shape. In the middle of the bucket, there is a metal plate that is called a splitter. Water just strikes on the splitter and it moving along the smooth surface of the curved blade. It is double hemispherical, so that the axial thrust that is balancing here, because when the fluid is passing through this region, the axial thrust occurring here, that is neutralizing, because the water is equally flowing through that hemispherical cup shaped buckets, so that the outlet angle of the bucket is in between 10 to 20 degree. In most cases it is 15 degree, so that the axial thrust can be neglected. And suppose m is the mass of the fluid striking with the velocity v. When the water is flowing along this curved blade, this angular velocity changing. So angular momentum m omega 1 changing to m omega 2. So here change in angular momentum. This rate of change of angular momentum, that is the impulse. That impulse force is responsible for the rotation of the turbine, so that it is called the impulse turbine. Here also this is the runner, and on the periphery of the runner number of buckets are provided here. That is, all the buckets are double hemispherical, and in the middle there is a metal plate, that is the splitter. And here you can see a nozzle is at that end. When we move this wheel, that nozzle is moving forward. We can change the position of the nozzle by controlling not nozzle, that a spear in the middle of that. This is the nozzle, and quantity of water is controlled by the spear movement. If the spear is forward, less quantity of water striking on the runner blade, and if the spear position is backward, more quantity of water striking on the turbine blade. That that is the governing mechanism. By controlling that movement of the spear, the quantity of water striking on the blade can be striking on the bucket can be varied. Here the turbine, when the water striking on the bucket, that is the angular velocity, angular momentum changing, so that the force is developing there, impulse force, and it produces a rotation there, so that the turbine shaft rotate. That is, that power p equal to t omega. T is the torque and omega is the angular velocity. This turbine is coupled with the generator shaft. In the turbine, power available is the mechanical power. This mechanical power is converting into electrical power, so that the turbine shaft connecting with the generator shaft. This is the generator and this is the turbine. So in order to couple these two, both should run at the same speed, then only they can synchronize. That speed is the synchronized speed. That synchronized speed ns is equal to 120 f by p. F is the frequency and P is the number of poles. In India, electric power producing with a frequency 50 hertz. So in order to produce that 50 hertz of frequency, turbine shaft should run at almost the same speed of the generator. That is the synchronizing. So in order to get that 20 hertz of frequency, 50 hertz of frequency, that is, we have to provide sufficient quantity of water to maintain that speed. For that, there is a governing mechanism. Governing means the turbine should run at a constant speed irrespective of the load variation. That is, when the load on the generator increasing, that is, more quantity of water has to be strikes on the turbine blade, so that turbine produces, that is, turbine more quantity of water striking on it. So due to the load variation, that is, if there is a load on the generator more, at that time, if the turbine is running at a rated speed, that is, the quantities load increases, so turbine should provide more quantity of water to maintain or to make up that load. And also, if the load on the generator decreasing, then the quantity of water has to be reduced. For that, a governing mechanism is providing. That governing